Hello and welcome back to my YouTube channel or Davig Structure Hub. This is the #1 channel for structural insight and a place where you learn, build, and innovate. Today I want to tackle an influence line question, and it is a question from a past paper, and this is July 2019. So it is question number 8A. So it reads, the figure 8 shows a continuous beam with a hinge at support B. Plot the influence line diagram for reaction RC and bending moment at D. Then question part B, determine the maximum bending moment at D when a 3-meter long UDL of 25 kilonewton per meter crosses the beam in 8 above from A to C. So this is the beam. It is a continuous beam. It has support A, which is a pinned, support B, a roller, support E, also a roller. So it has a hinge at B, and the dimensions are as follows: 2 meters from A to B, again 2 meters from B to C, 2 meters from C to D, and 4 meters from D to E. So let's see how you can tackle such a question. So solution. So we will begin by part A, whereby in part A, we have been told to plot the influence line diagram. So influence line diagram for reaction C, for RC, and then bending moment at D. So let's begin with influence line for RC. For us to draw the influence line diagram for RC, we are supposed first to determine reaction RC. And then after determining reaction RC, we will calculate ordinate for RC. Then after calculating the ordinates, then we'll be able to draw the influence line diagram. So let's see how we'll calculate the reaction RC. So for us to determine reactions for this beam, we will first divide this beam into 2. So I want to divide this beam into 2 where we have a hinge. So we will have a force or a reaction which is RB. So this reaction is on the left side of the hinge. And then we'll have an opposite reaction of equal magnitude, which is again RB in the downward direction, such that we will end up having section A and RB from A to RB on the left, and then RB on the right to E. So having done so, I will introduce a unit load at any point between A to B, and the distance will be X. And this is 1. So the first thing to do, say that let the unit load roll from A to B. So this is part of the solution. And then you will say divide the beam into 2 at B, where we have a hinge at B, so that we may have A reaction RB on the left in the upward direction and another one which is again RB of the same magnitude in the downward direction. So after having done so, you can now say, or you can sum moment at any point, summation of moment at a point. Let's consider RB. At RB is equal to 0. So in which direction is RA moving in reference to RB? So this is RA, this is RC, and this is RE, like that. So summation of moment at RB is equal to 0. So it means this RA is moving in clockwise direction in reference to RB. So we have RA times 2. So this is 2 RA. And then we will come to this 1 unit load. So this is 1 unit load is moving in which direction? So this one is moving in anti-clockwise direction. So you will say minus 1, then you open the bracket. The distance from here, from where the 1 unit load is acting to RB, it will be 2 minus x, then is equal to 0. So here you'll have 2 RA minus 2 minus x is equal to 0. So this one will cross to the other side, so it will change from negative to positive. So we'll end up having 2 RA is equal to 2 minus x. To get RA, divide both sides by 2, both sides by 2. So RA, which imply RA is equal to 2 minus x all over 2. So that is RA. Allow me to clean here. Now we know that RA is equal to 2 minus x all over 2. So let's find the ordinates for this RA. So we will say that at A, when the load is at A, so at A, when the load is at A, x is equal to 0, which imply RA is equal to, so you will substitute x with 0, so you'll end up having 2 minus 0 over 2. So RA will be 1, like that. Again, you will come to B and say that at B, where x is equal to 2, it implies that RA is equal to, now you will take 2 and substitute it where x is. So 2 minus 2 is 0, over 2 is 0. So this one is equal to 0, like that. So we are done with reaction A. Now, come and apply uh, this equation of equilibrium, and it said that summation of upward forces is equal to summation of downward forces. So the upward is RA. Remember, we are considering AB only. So for the AB, the upward forces is RA plus RB, and the downward forces is only one unit load. So we know that RA, we already have RA, so it means RB is equal to 1 minus RA, because RA will cross to the other side. So 1 minus 2 minus x all over 2. So this is over 1. The LCM is 2. So we'll end up having 2 minus 2 into 2 is 1, minus 1 times 2 is 2, minus 2, then plus x. So RB is equal to x over 2. So there is no need to calculate the ordinate for RB, because RB is a hinge, and it will only help us to calculate reaction at A and at C. And let's now some moment about RE, so that we can get RC. Summation of moment, we are now summing at RE so that we can get RC. So summation of moment at RE is equal to 0, like that. So it means that RA is moving in clockwise direction. As you can see, this is clockwise direction. So we have RC times the distance from RC to RE, which is 2 plus 4, that is 6. So we have 6 RC. Then we will come to this RB on the left, no, on the right of this beam, which is moving in the downward direction. So it is moving in which direction? In reference to RE. So this is anti-clockwise. So minus RB times the distance from here to here. This is 2 plus 2, 4 plus 4, 8, is equal to 0. So we have 6 RC minus 8 RB is equal to 0. But RB is equal to, we already have RB x over 2. Now we'll substitute RB with x over 2. So 6 RC minus 8 times x over 2 is equal to 0. So 6 RC minus 4 x is equal to 0. So 2, 1, 2, 4. So it means RC is equal to, 4 will cross to the other side, is equal to 4x over 6. So which is equal to 2x over 3. So this is RC. This is RC when the load is when the one unit load is in A or is in between A and B. So remember to keep this 1 and 0 for the influence line diagram. So let's go to the ordinate for RC. Ordinate for RC. So ordinate for RC. So for RC, when the load is at A, so X is equal to 0. So when the load is here, X is equal to 0, which imply RC is equal to, so you'll replace this X with 0. So we'll end up having 2 times 0 over 3, which is 0. And then when the load is at B, X is equal to 2, which imply RC is equal to 2 times 2 over 3. So this X replace it by 2. So 2 times 2 over 3. So this one is equal to 1.33. 1.33. Let's proceed. Allow me to clean here. Now, because we have calculated RC, we are also supposed to calculate RE. And how are we going to calculate RE? When the load is still between A and B. So to calculate RE, we will again use this expression or this equation. Summation of upward forces is equal to summation of downward forces. So the upward forces, if we can consider between RB on the right and RE, the upward forces is RC plus RE, and the downward forces is RB. As you can see, this RB is on the downward forces, and then the upward forces is RC and RE. So we already know the RC. So to get RE, we will take RE is equal to RB minus RC. So this will cross to the other side. So it will change sign from positive to negative. So this one is equal to, also we already have RB. So RB is equal to, we have already calculated this. Let me check it for you. So this is 0.5 or X over 2 minus RC, which is here. RC is 2 over 3 X. which imply RE is equal to X into bracket a half minus 2 over 3. So you factorize X. So this one is equal to minus X over 6. Minus X over 6. It means RE, if you get minus X over 6, it means if the load is in between A and B, then this reaction should be on the top of this beam, not in the upward direction. So it means RE is in the wrong direction. So RE is in the wrong direction. Remember, it's in the wrong direction when the load is in between A and B. So we are rolling this load from A up to E. So we are rolling it from A up to E. And we begin with A to B. And then we will proceed to B, C, E. So the load will roll from B to C to E after A, B. So if we change the direction, of the reaction, this is how the beam will be. So this is RE, and this is RC, and this is RA. And the distance or the dimension are as follows. So this is 2 meters, and then 4 meters. And then 1 unit load is here. So this is X, like that. So we now proceed to, now we are done when the unit load is in between A and B. We want now to proceed when when we let the unit load roll from B to C to E. But before then, let's calculate the ordinate of this RE. Let's calculate the ordinate of RE. Ordinate RE. So when the load is at A, X is equal to 0, whereby RE is equal to negative 0 all over 6, which is equal to 0. So when the load is at B, so X is equal to 2, like that. So RE is equal to minus 2 all over 3, no, all over 6, minus 2 all over 6, which is equal to negative 0.33. So we are done. As I said earlier, we are done with RA, RB, RC, and RE when the load is in between A and B. Now we want now to allow the load to roll from B to C and to E. We want now the load to roll from B to C and to E. Let move the unit load to B, C, E at a distance X from point A. So allow me to draw again the beam. So now the load is here. So this will be the distance X. And remember, the load is 1 unit load. So this is RA, this is point B, this is RC, and this is RE, like that. So reaction, if the load moves from B, C, E, then it means RA is equal to 0, and also RB RA is equal to 0, and also RB. So it means at here there will be no effect of this load. So at B and A there will be no effect of this load. So the reaction will be 0 at RA, and the reaction will be 0 at RB. So we are now supposed to calculate reaction at C, RC, and reaction at E when the load is at CE, when the load is at CE, So here it should be let move the unit load to CE at a distance X from point A. So RA is equal to 0, and also RB is equal to 0. Now summation of moment at RE, summation of moment at RE is equal to 0. So this one will help us to get RC. Remember, when the load is when the load has already rolled from B to C to E. So it means this RC will be moving in clockwise direction. So it will be RC times the distance. This is 2 plus 4. This is 6. So 6 RC. And then we'll come to this one unit load is moving in anti-clockwise direction. So minus 1 into bracket the distance from here to here. So you will take the total distance from here to here minus x, which is 2 plus 2, that is 4. 4 plus 2, 6. 6 plus 4, 10. So it will be 10 minus x is equal to 0. So 6 RC minus, if you open the bracket, this is 10 minus x. So open without a negative is equal to 0. Then the whole of this will cross to the other side. So we'll end up having 6 RC is equal to 10 minus x. Divide both sides by 6, which imply RC is equal to 10 minus x all over 6. So this is RC. Now again, you are supposed to find the ordinate for RC. So ordinate for RC, ordinate for RC. So when load is at, now we are at this point, this is C. When the load is at C, x is equal to 2 plus 2 is equal to 4. Means RC, the ordinate of RC is equal to 10 minus 4 all over 6. So this one is equal to 1. So 10 minus 4 is 6. 6 over 6 is 1. And when the load is at E, x is equal to 10. So this is 2 plus 2, 4 plus, this is 2 plus 2, 4. 4 plus 4, 6. 6 plus 4, 10. So it will be 10 minus 10 all over 6, which is equal to 0. Now at B, x is equal to 2. Here at B, x is equal to 2. So RA will be, so you will substitute x here in this formula with 2. So RE will be 10 minus 2 over 6, which is equal to 1.33. We now proceed to RE when the load is in between C and E. Remember, these ordinates are very important because we will use this ordinate to draw our influence line diagram for reaction C. So we know that summation of upward forces is equal to summation of downward forces. So summation of upward forces is equal to summation of downward forces. So the upward forces is RC plus RE, which is equal to 1, like that. So RC, we already have RC, so it means RE is equal to 1 minus RC, which is 10 minus x all over 6. So the LCM is 6. This is over 1, so it will be 6 minus 10 plus x. So this one is equal to 6 minus 10 minus 4 plus x all over 6. So you can interchange by saying that x minus 4 over 6. So this is RE, like that. Again, you want now to calculate the ordinate for RE. So at B, x is equal to 2. So at B here, x is equal to 2. So therefore, RE is equal to 2 minus 4 all over 6. So this one is equal to, so this is negative 0.33. So this is at B when x is equal to 2 at B here. And then we move at C. At C, x is equal to, at C x is equal to 2 plus 2, this is 4. So therefore, RE is equal to 4 minus 4 over 6, which is equal to 0. And then you move at E. At E here, when x is equal to the whole of this length, which is 10. Allow me to clean here. So at E, x is equal to 10. So it therefore means RE is equal to 10 minus 4 over 6, which is equal to 1. We are now done with what we call reactions together with its coordinates. Now it is time to draw the influence line diagram for reaction C. Now these are all the ordinates for influence line for RC. We have already calculated this. So what you are now supposed to do is to draw the influence line diagram for RC. So we'll now draw the baseline. So this will be the baseline. And this is the influence line diagram for RC. So we begin at A. At A is 0. So here is 0. And then at B is 1.33. So we have to B, the same value, 1.33. This is 1.33. And then we come to RC. RC is 1, like that. And then at E is 0. Here is 0. So we will connect the dots or the points. Like that. So this is positive. So this is the influence line for RC. Now we want now to calculate the moment. We want now to draw the bending moment at D. But before we draw the bending moment at D, we are supposed to calculate the values of bending moments at various points. So let's see how we can do that. Allow me to clean here. So part B of the question is to draw the influence line diagram for at D. Influence line diagram at D. But before then, let's calculate the let's calculate the moment at various points. So again, I will draw the beam. So this is the beam. Two meters, 2 meters, 2 meters, and then 4 meters. And this is point D. So we are supposed to draw the influence line diagram for the moment at D. For the moment. At D. So if this is the beam, so first let's keep the unit load between A and B. So first, let's keep the unit load between A and B. This is A, B, C, E. So MD, if we keep the unit load between A and B, so MD is equal to minus RE times 4. So it will be this RE times, because moment is force times perpendicular distance, and we are at this point, and the unit load is in between A and B, so the moment will be force times perpendicular distance. So at this point, we have this RE, so it will be moving in this direction, which is minus, it is moving in anti-clockwise direction, so it is minus RE times the distance from here to here, which is 4. But RE is equal to, we have already calculated RE. We calculated RE when the load is between A and B. And the expression for RE was minus x over 6. So MD is equal to RE, which is minus x over 6 times 4, which is equal to minus 2x all over 3. So that is MD, minus 2x over 3. Let's now get the ordinates. So when x is equal to 0, so x is at A, when x is equal to 0, so this is point A. Let me write it in brackets. So this is at A. So MD is equal to minus 2 times 0 all over 3, which is equal to 0 kilonewton meter. MD is equal to 0 kilonewton meter. We now proceed to when x is equal to 2. So this is point B. This is point B. MD is equal to minus 2 times 2 all over 3. So this one is equal to minus 1.33 kilonewton meter, like that. We now move the load from AB to CD, from AB to CD. Again, keep these values, 0 kilonewton and negative 1.33, because we will use these values to draw the influence line diagram for the moment at B. Let's keep the unit load between C and D. Between C and D. So MD will be minus RE times 4. Again, this reaction at E will be moving in anti-clockwise direction, so it will be minus RE times 4. But remember, RE is equal to x minus 4 over 6. So this is RE when the unit load is between C and D, and this expression is already in our calculation. So it is like that. So it means MD is equal to RE, which is x minus 4 over 6, so minus x minus 4 over 6 times 4. So this one is equal to minus 4x plus 16 all over 6, like that. Minus 4x plus 16 all over 6. If we open the bracket. So let's now find the ordinates. Let's find the ordinates. So when or at C, here at C, x is equal to 2 plus 2, which is equal to 4. Therefore, MD is equal to 4 minus 4 times 4 plus 16 all over 6, which is equal to 0, which is equal to 0. like that. At D, x is equal to, now at D, x is equal to 6. X is equal to 6. So therefore, MD is equal to minus 4 times 6 plus 16 all over 6. So minus 4 times 16 all over 6. Minus 4 times 6 plus 16 divided by 6. So this one is equal to negative 1.33. Negative 1.33. Allow me to clean here. Remember to keep these ordinates because of the diagram for the moment at D. Now let's keep the unit load. Keep the unit load between D and E. Now the unit load is in this portion. So it means we now consider RC. This RC is moving in this direction toward D. So moment at D is equal to MD is equal to RC times the distance from here to here times 2 times 2. But RC is equal to, we have already calculated RC, but RC is equal to, for the RC is when the unit load is between D and E for the reaction. So RC is equal to 10 minus X all over 6. Now MD is equal to 10 minus X all over 6 times 2. So this one is equal to, here 1, here 3. So it's equal to 10 minus X all over 3. Let's now obtain the ordinates. Ordinates. At D, X is equal to 6. X is equal to 6, which imply MD is equal to 10 minus 6 all over 3. So this one is equal to 10 minus 6 all over 3, 10 minus 6 divided by 3. So this one is equal to 1.33. 1.33. At E, x is equal to, at E here, x is equal to 2 plus 2 plus 2 plus 2. So this is 10, which imply MD is equal to 10 minus 10 all over 3. So this one is equal to 0. So this one is equal to 0. So after having done so, we can now draw the influence line diagram for the moment. So allow me also to clean here. These are the ordinates for a moment at D. You have already calculated this. So what we need to do is to draw the moment, the influence line for moment at D. So let's draw the baseline. So let's draw the baseline. So that is the baseline. So we will begin by A. A is 0. So here is 0. And then at B, negative 1.33, around there. So 1.33, this is negative. And then at C is 0. At C is 0. And then at D, negative 1.33. At D, negative 1.33. 1.33. Again at D, positive 1.33. And then 0. So it will go like this. You join the points. Like that. So that is how you draw the influence line for the moment at D. So this is the negative, negative, positive. So the last question, determine the maximum bending moment at D when a 3-meter long UDL of 25 kilonewton per meter crosses the beam in 8A above from A to C. So if a load of UDL, which is 25 kilonewton per meter, will cross from A to C, then we are supposed to determine the maximum bending moment. So let's introduce the load here. So the load is 25 kilonewton per meter, and it is spanning 3 meters. So you can make 1.5, then 1.5, 1.5. So the maximum bending moment will be at this portion, because this is positive. So extend the line. So we are supposed to calculate the moment for this shaded region. So before you calculate the moment for this shaded region, let's first calculate this distance from here. From here, this distance x. And I will show you how to calculate this distance x. Allow me to clean here. So if we use the similar triangle, we'll compare this distance, which is 1.33, all over this one, which is 4, is equal to x all over 4 minus 1.5, which is 2.5, which imply x is equal to, you cross multiply. So x is equal to 1.33 times 2.5 divided by 4, 0.83. 0.83. So to get the maximum bending moment is equal to, the area of this will be a half into the sum of two parallel sides, that is 1.33 plus 0.83 times the length is 1.5 then times 25. So this one is equal to 0.5 times 1.33 plus 0.83 times 1.5 times 25. So this one is equal to 40.5 kilonewton meter. And that marks the end of this question. So thank you for your time. If you have not subscribed to this channel, please subscribe and hit the notification bell so that you may be the first person to be notified when I upload a video. So thank you for your time, and we meet again in my next session.